Hello everyone. This is another video, lecture 4 on relativistic electrodynamics, and here we will be solving some numericals from Griffith, David J. Griffith, and which will clear some of your concepts. Right, we will try to solve the problems available in Griffith book. Okay, so let's start. We will slowly solve. You first try to solve it. After that, if you cannot solve, I will do it. Okay, you first try. Right. So this is your first question here. Let S be an inertial reference frame. Use Galileo's velocity addition rule. Okay, and suppose that S dash move with constant velocity relative to S, so that S dash is also an inertial reference system. Okay, so it is saying if S dash moves with constant velocity relative to S, so that S bar is also an inertial reference system. Okay. Conversely, so that if S bar is an inertial system, then it moves with respect to S at constant velocity. Okay, so this is the question, and we have to solve it. Okay, see how do I solve it? See, suppose in S inertial frame, let there be a particle with velocity u. Okay, u is the velocity of the particle, velocity of a particle in S frame. Okay, in S. Okay, use Galileo's velocity addition. Okay, u bar will be the velocity u bar. Sorry, u bar will be the velocity of the particle in S bar. Okay, and v will be the velocity of S bar with respect to S. Okay, S bar with respect to S. Alright. Yeah, this is a v. So Galileo's velocity addition rule says that what? Galileo's velocity addition rule. Galileo's velocity addition rule is what? It is u is equal to u bar plus v. Okay, that was v. So for free particle, u is constant. Okay, that's Newton's first law in S. So for free particle, you can say for free particle, u is constant. Okay, so first question. Let's go to the first question. That is, suppose that S dash moved with constant velocity relative to S. Okay, so that is your velocity v. So that S dash is also an inertial reference system. Okay, so v, it is saying v is constant. It is just it's saying constant velocity. So v is your constant. It's saying v is constant. So if v is constant, okay, if v is constant, then your u bar, that is u minus v, u minus v will also be constant, right? U minus v will be constant. Yeah, so u bar will be constant, or you can say u will also be constant. Yeah, okay, so hence S will be what? S will be your inertial frame. All right, got it? Yeah. Okay, what is the next question? If S in a so that if S bar is an inertial system, then it moves with respect to S at constant velocity. Okay, S bar is an inertial system. So if S bar is inertial, so this is your actually U is equal to U bar plus V. So this is constant. Okay, then only S will be constant inertial. So if S bar is inertial, if S bar is inertial, then if S bar is inertial, then U bar is also constant. U bar is also constant. So V will be what? U minus U bar will be constant, which is the question, right? It moves with constant velocity with respect to s. All right. I hope you understood this one. Yeah. Let's move to the next question. That is an illustration. Okay. Principle of relativity, classical mechanics. Consider the following generic collision in inertial frame S. A particle A, velocity UA, hits particle B with velocity UB. In the course of the collision, some mass robs of A, mass is lost from A, and onto B. It's lost onto B. We are left with particles C, mass MC, velocity UC, and velocity D. Assume that momentum is conserved in S. Okay. So prove that momentum is also conserved in initial reference frame S bar, and the which moves with velocity V with respect to S. So let's write down all the data that is given in the question. First of all, we'll do that. So write down all the data that is given in the question. So what is it? See, first MA is a particle in reference frame S. There is your A and B. They collide with each other, and after collision, some mass of A goes to B and all that. We are left with particles what? C and D. Okay, in the same frame. C and D. Yeah. So the momentum is conserved in S. Okay. So if momentum is conserved in S, we can put the momentum before collision. Momentum before collision is equal to momentum after collision. Momentum after collision. Okay. Alright. So we know U is equal to what? U bar plus V. So we can do it here. So UA will be UA bar plus V. Yeah. So MA UA bar plus V is MB UB bar plus V is equal to MC UC bar plus V is MD UD bar plus V. Okay, bar plus V. What is this V? V is the one which moves relative velocity V with respect to S. Okay, so that's why V is constant for everything. So let's open this. Let's open this. So it will become MA UA bar plus MA UB MAV plus MA UB bar plus MAV MBV. So plus okay, is equal to MC UC bar plus MC V plus MD UD bar plus MD V. Okay, this is the equation for it. So suppose mass is also conserved in the equation. If mass is conserved, assuming mass is conserved, assuming mass is conserved, what will happen? If mass is conserved, Ma plus Mb is equal to Mc plus Md. Okay, so mass is in this. So we can do what? So if you see, so Ma plus Mb, okay, I can take common here. So see, Ma Ua bar plus Mb Ub bar plus Ma plus Mb whole into V is equal to MC UC bar plus MD UD bar plus MC plus MD whole into V. So here MA plus MB is equal to MC plus MD. So they can cancel each other out. So MA UA bar plus MB UB bar is equal to MC UC bar plus MD UD bar. Is that alright? Is that alright? Yeah. So see, this is isn't it the moment velocity in S bar, velocity in S bar, velocity of C in S bar, velocity of D in S bar. So momentum is conserved in S bar. That's the question. Okay. Prove that momentum is also conserved in S bar. So that is momentum is also conserved in S bar. Is that all right? Yeah. Oh, okay. What is the next question? Suppose the collision is elastic in S, so that it is also elastic in S bar. So momentum is already conserved. So what is left for elastic collision? Kinetic energy should be conserved. Okay. So elastic collision, kinetic energy should be conserved, right? So we can write again ma square half mb square plus mbub square is equal to ma mcuc square plus half mdud square. Yeah. So again we will put ua is equal to ua bar plus v, like that we will put. Okay, v everywhere. So again half ma ua bar plus v whole square plus half mb ub bar plus v whole square plus is equal to half mc uc bar plus v whole square plus half md ud bar plus d will v whole square. Okay, so now what will you do? We'll just open the brackets. We'll open the brackets. So if I open the brackets, I will get what? I will get those terms. Half ma ua bar square plus 2 ua bar dot v plus v square plus half mb ub bar square plus 2 ub bar dot v plus v square is equal to half mc uc bar square plus 2 uc bar dot v plus v square plus half md ud bar square plus a 2 ud bar dot v plus v square. Okay, so this is what we got. So we can now again we can equate them, like expand them a bit, and if we expand them, so we will see the middle terms will be conserved, will be used for like conservation of momentum. Okay, conservation of these terms will be cancelled out kind of by conservation of momentum. So we will get, we can easily prove from here that half ma ua bar square plus half ma mb, you can check it yourself, u bar square is equal to half mc uc bar square plus half md ud bar square. So that will be their final expression. So from here we can prove that they are elastic collision. Okay, I hope you understood. Okay, okay. Let's move to the next question. Yeah. What's the percent error introduced when you use Galileo's rule instead of Einstein's rule with VAB is equal to 5 miles per hour, VBC is equal to 50 miles, 60 miles per hour. Okay. So percent error introduced when you use Galileo's rule, that is this and this. Okay. So Galileo's rule is one and Einstein's rule is one. So we will separately use them. Okay. So see your VAB here. VAB is your 5 miles per hour. VBC is your 60 miles per hour. Okay. So your according to Galileo, the velocity will be simply added. Okay. So V whatever that is, V Galileo, so VG. So simply they will be added VAB plus VBC. So it will be 5 plus 60, that will be 65. Okay, 65 miles per hour. So according to Einstein, what will happen? Einstein has a different rule, that is VE, suppose if I write, so it will be VAB plus VBC divided by 1 plus VAB into VBC divided by C square. Okay, so see 5 plus 60 divided by 1 plus 5 into 60, that 300 divided by C square. So this is your answer for this one, Einstein. Okay, so after putting all the values, we will get, let me directly write it, 6.7 into 10 to the power 8 miles per hour. Okay, so this is what I will get, and if we can calculate the percentage also, simply very simple, Vg minus Ve divided by Vg into 100, yeah, you will get the percentage. Okay. Next question. Suppose that it could run at half the speed of light down the corridor of a train, going three quarters of the velocity of light. What would your speed be related to the ground? Okay. This is again we can use that. So let's use the velocity addition. Sorry, this one, Einstein's this velocity rule. Okay. So your speed is what? Of the speed of light. So suppose v a b is c by 2. Okay. The train speed is VBC, suppose, is 3 quarters. That means 3 quarters means 3 by 4. Okay, 3 into 1 quarter is 1 by 4, 3 quarter. Okay, so what is your speed related to the ground? Which ground? Okay, U I have taken, this is A as U. Okay, that means yourself. B is your train and your C is the ground. Okay, yeah. So your velocity with respect to train is c by 2. Train's velocity with respect to ground is 3 by 4 c. So we have to find this. What is speed related to the ground? That is VAC. Okay. So VAC will be simply VAC will be simply VAB plus VBC divided by 1 plus VAB dot VBC divided by C square. Okay. So what is there in the question? Yours is c by 2 plus 3c by 4 whole divided by 1 plus c by 2 into 3c by 4 divided by c square. Okay, so for this 5c by 4 whole divided by this becomes 1 plus 3 by 8, right? Plus 3 by 8, so 11 by 8, 5c by 4 divided by 11 by 8. Okay, so this becomes 2, 2 goes up and becomes 10c by 11. Okay, so that will be answer. VAC will be 10c by 11. Right? So velocity Einstein's rule will be applied. Prove equation 2.3. This is okay. We don't have the equation 2.3 here, so let's leave this one. Okay. Okay. Next question. Okay. As the outlaws escape in their getaway car, which goes 3 by 4 c. Okay. Let me zoom it a bit. Yeah. 3 by 4 c. The police officer fires a bullet from the pursuit car, which only goes 1 by 2 c. The muzzle velocity of the bullet relative to the gun is 1 by 3 c. Does the bullet reach its target according to Galileo? According to Einstein? That means it's saying, will the bullet reach the other car in which there are thieves? Okay. So again, that like bullets velocity must match the relative velocity. So we will calculate according to Galileo and according to Einstein. Again, very simple question. Suppose velocity of like the thieves with respect to ground. Suppose is 3 by 4. Okay. The velocity of the police with respect to thief is your what? 1 by 2 c, suppose. So velocity of bullet we have to calculate. So we will do again same kind of velocity of bullet will be what? VPT plus VAB VBC, you can also take no problem. Okay, VTG divided by 1 plus this into this divided by C square. Okay, so see this is 3 by 4 and 1 by 2 by 4, that's 5 by 4c divided by 1 plus um, 1 plus 3 by 8. Okay. So this becomes 11 by 8, and 11 by 8 goes up, 5 by 4 into 8 by 11. So this becomes 10 by 10c by 11. So 10c by 11 is the velocity of the bullet. Okay. Yeah. 12 or something else. Yeah. So this is according to Einstein, right? This is according to Einstein. So if you see here, will 10c by 11. Okay. So um, okay, let me do it again. You may have been confused with this. Okay, let's do the according to the question that below. According to Galileo, we'll start with Galileo. Okay, we'll start with Galileo. So first we'll start with Galileo. So see, okay, velocity of bullet. I will write it properly with respect to ground. Respect to ground. Okay, velocity of bullet with respect to ground is how much? How much it's written? According to Galileo, they'll be just simply added, right? Which is 1 by 3 plus 1 by 2. So 1 by 2 plus 1 by 3c. Okay, see in the question, module velocity is 1 by 3, this one. 1 by c, 1 by 2, 1 by 3. So they will give me, this is your 6. So this is 3, 5c by 5c by 6. Okay. Velocity of the car, velocity of the thief's car or getaway car. Velocity of the getaway car is how much? It's then 3 by 4. Okay. 3 by 4. Okay. So if we kind of equate them, suppose let's make it 10c by 12. This is your 6c by, okay, this is a 9c by 12. Okay, 9c by 12. Okay, see. So the velocity of car is this one. Velocity of the bullet will this one. That means the velocity, bullet velocity is greater than the velocity of the car. That means the bullet will reach the car. Okay, because bullet is going at suppose 20, 100. Car is going at 90. So of course bullet will catch the car. If the bullet's speed was 80, it couldn't have reached the car. Okay. If you are faster than someone, you will cross him. If you are slower than him, you cannot cross him. That's the simple basic form of thing. Okay. So that's why the bullet will reach the car according to Galileo. Okay. So right now, according to Galileo, bullet will uh, target the car, target or reach the car according to Galileo. Okay. What will happen according to Einstein? Okay, so Einstein, we have done it. VE Einstein's formula, like this one into this one. So 1 by 2c plus 1 by 3c divided by 1 by 2c, 1 plus 1 by 2c into 1 by 3c divided by c square. I had done it wrong in the previous one, okay, earlier. So this is 6, and this becomes 5c by 6 divided by 1 plus 1 by 6, that is 7 by 6. Yeah, 7 by 6, 6 cancel out. So 5c by 7, right? 5c by 7. So if I kind of okay, other one is velocity of bullet is how much? Velocity of the getaway car is how much? 3c by 4. So let's kind of equate them. Okay, if I multiply 7 here to equate the denominator, only then we can know 7 here 4. So see, so this is less. So velocity of the bullet here is less than the velocity of the car. That means the car is 100 kilometer per hour, the bullet is 90. Suppose. So the bullet won't be able to cross the car or raise the car, right? Because car is faster than it. Okay. So according to Einstein, the bullet does not reach the car. Is it correct? Is it correct? Is it alright? Okay. Next question. This is a very easy question. I won't do it. I have done this kind of question now. See, a laboratory experiment, I will zoom it for you. A laboratory experiment. Okay. A muon is observed to travel 800 meter before. Sorry. Something has to before disintegrating. A graduate student looks up the lifetime of a muon as 2 into 10 to the minus 6 seconds. Concludes that its speed was this much. So faster than light. Is it faster than light? Identify the student's error. There must be some error. Find the actual speed of this. Okay. So please do this one. This is for you. You can take your time or you can take it as homework. And do this one for by yourself. Okay. Yeah. Oh. Next again. Rocket ship leaves Earth at a speed of this. Okay. When a clock on the rocket says 1 hour has elapsed, the rocket ship sends a light signal back to Earth. According to the Earth's clock, okay, when was the signal sent? Right? So see, the rocket clock actually runs slow, isn't it? Rocket clock runs very slow because of the time dilation. Because the speed is very fast. So because of time dilation, rocket clock will moves kind of slow. It's not like completely slow. Okay. So from there we can okay. Suppose so there from there we can calculate. Okay. So we know the this one the proper time del tau is equal to what? T by del t by 1 minus v square by c square root over, right? So del t is your what when a clock says 1 hour has elapsed. Okay, so that means okay, okay, let's do it. Okay, let's first calculate this gamma. Gamma will be what? 1 minus 9 c square by 20. Okay, 9 by 25. C square will cancel out. 16 by 20 is 4 by 5. So 5 by 4 del t. Yeah, 5 by 4 del t. So 5 by 4 del t. So what is del t here? When a clock on the rocket says 1 hour has elapsed. Okay, yeah. So 1 hour has elapsed. So I can put in place of del t what 1 hour. Okay. So this is the time in the rocket. This is the time on Earth. The proper time. Just a second. यहाँ पे rocket बन गई है. Del t. So del t is a what? Del t is a 1 hour. So 5 by 4 into 1 hour suppose is 60 minutes. So this is 1575 minutes. So the clock on Earth that is a proper time shows what 75 minutes, that is 1 hour 15 minutes. Is that all right? On Earth. Is it all right? Yeah, very good question. According to Earth's clocks, how long after the rocket left did the signal arrive back on Earth? Okay, by Earth observer, rocket is now at a distance what? What is the distance you can measure? Distance we can measure. Okay, distance will be what? Time into speed. Time into speed. So this is the time, 75 minutes. Speed is your 3 by 5 c. 3 by 5 c. So from there you can calculate easily. So, so distance. So 3 by 5 c speed, time that is 75 minutes. That means, okay, I have to convert it into suppose hour. No, no, sorry. Sorry. This is 60 minutes. 1 hour, yeah, 1 hour. So this is 3 by 5 c hour. Okay. Three quarters of a light hour, we can say. Away from away. So light signal will therefore take 3 by 4 hour. 3 by, did I do any wrong? Okay, okay, sorry. This is correct. So 75 minutes. 75 minutes. Okay. So 3 by 5 C into this is actually your 5 by 4 hour. Yeah. So 3 by 4 hour. 3 by 4 C. Uh, so light will take 3 by 4 C. 3 by 4 light hour. It will take. Okay, so light signal will take 3 by 4 hour to return to Earth. Okay, you can write light signal will take 3 by 4 C hour, 3 by 4 hour to return Earth. This is called light hour, okay? Seen to Earth. Since it, so as it left 1 hour 15 minutes after the departure, so light signal which reached the Earth at 2 hour after takeoff. Okay? Got it clear? What's the next question? According to rocket also, how long after the rocket did the signal arrive back on Earth? How long? This question is left for you. This is your homework. I've done it now. I did too. So this is it. Alright. Yeah. So these much questions for today, and we'll be solving more in the upcoming sessions. Right. I hope you understood. Yeah. Right. Thank you very much. Thank you.